All right, so we've gotten a look at one-sided limits by looking at the unit step function. Now we're going to define these one-sided limits in more general terms. Okay, so here are our definitions. We say that the left-hand limit, so left-hand limit of f of x as x approaches c equals L if f of x gets close to L as x gets close to c from values that are less than c. Okay, so that idea of values that are less than c. Here's a little number line. Here's your c. So we are coming in from this direction. We are moving towards x equals c because that's what it means to approach. But we're coming from values that are less than c. So that's why we call this the left-hand limit, because if you put your hands on the number line, your left hand is over here. All right, so left of c, and then you approach. All right, and this one, this notation that we had seen a little bit of before, this is the limit as x approaches c from the left of f of x equals L is what this is defining. Okay. And then, in contrast to that, we are going to have the right-hand limit. And as you would suspect, it's going to be defined very similarly, just from the other direction. So the right-hand limit of f of x as x approaches c equals L if f of x gets close to L as x gets close to c from values that are greater than c. Okay, so opposite side, of course. All right, so if our little number line looks like this, the values that are greater than c would be all over here. So we're going to come in from that direction. We're approaching c, but from the right. Okay, so you start to the right and you move in towards c. That makes a right-hand limit, the values that are greater than c. And so notation for this, what we're really writing, is the limit as x approaches c from the right, that little plus, f of x equals L. Okay. So limit as x approaches c from the right of f of x equals L. Or you could read that as the right-hand limit of f of x equals L. You could also say it that way. That's totally fine. Okay, so we have another theorem that goes with these definitions that also reflects back to what we saw with the unit step function. And this theorem says for a general limit to exist, we need to approach the same limit from both directions. That was part of our original definition of an overall limit, was that we're approaching some x value from both sides. Okay, so approach the same limit from both directions. The left hand and right hand limits must be equal. Okay, So that's why we were able to see that the limit of the unit step function as x approached 0 did not exist because the left-hand limit and the right-hand limit were two different values. So that really all goes together here. Okay, in mathematical notation for this theorem, we can say that the limit as x approaches c of f of x equals L if and only if, so this makes a very strong statement here, if and only if the following is true. The limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. So those are both equal to L. Okay, so this if and only if statement in the middle there, yeah, like I was saying, that is a very strong statement. So if this is true on this side, the limit as x approaches c of f of x equals L overall, this other side has to also be true. So if this is the overall limit, you automatically get these two one-sided limits for free. It's part of this theorem. Both of those limits have to equal L. And then it also goes back the other way. If you know both of those limits exist and they both equal L, then you automatically know that the general limit exists and it equals L. Okay, these are two things where if you have one side that's true, the other side is true instantly.